In this lecture, we're going to talk about transformers. In November 2022, we witnessed a watershed for AI, the introduction of ChatGPT. Technologically, not much changed. AI researchers who had been paying attention didn't see anything that they didn't know could be done. But for the world at large, the fact that the existing technology was put into a friendly environment and made accessible to all woke people up to what was now possible. Behind the scenes, the fundamental technology behind ChatGPT, the transformer, had been introduced in 2016 and had been steadily maturing until 2021. Over the years, we began to see what was possible when these models were trained at huge scales. In this lecture, we will look at the surprisingly simple mechanism that powers transformer models like ChatGPT, self-attention. And we will take a broad look at how it's built into models containing hundreds of billions of parameters. At heart, transformers are sequence models. We've seen two examples of non-trivial sequence-to-sequence layers so far: recurrent neural networks, RNNs, and convolutions. RNNs have the benefit that they can potentially look infinitely far back into the sequence, but they require a fundamentally sequential processing, making them slow. Convolutions don't have this drawback. We can compute each output vector in parallel if we want to. But the downside is that they are limited in how far back they can look into the sequence. Self-attention is another sequence-to-sequence layer, and one which provides us with the best of both worlds: parallel processing and a potentially infinite memory. To explain the basic idea, we will strip it down to its essentials. We will call this simple self-attention. This will show the simplicity of the operation and allow us to understand its fundamental properties more easily. Then we will add some bells and whistles to define self-attention as it's practically used. These added features don't change much about how self-attention operates fundamentally, but they make it a bit more powerful in practical use. As we said before, self-attention is a sequence-to-sequence layer. That means its job is to consume a sequence of vectors and to spit out another sequence of vectors. At heart, the operation that does this is very simple. Every output is simply a weighted sum over all the inputs. We multiply each input by a weight and then sum them all up. So when we're computing output y3, we have a weight w3i for every possible input, and we then multiply each input vector by its weights and sum these products together. The result is y3. In order to keep the magnitude of the output stable, we ensure that the weights are positive and that they sum to 1. This is not unlike the feed-forward network we've seen already, except that the inputs are now vectors instead of numbers. However, the fundamental trick of self-attention is that the weights in this sum are not parameters. They are derived from the input. Here's how that's done. The output vector y, as we already said, is a weighted sum over the inputs. The weights are then derived from the similarity between the input xj, for which we're computing the weight, and the input xi, whose position corresponds to that of the current output vector yi. Now, the more similar these two vectors are, the higher the weight, and we express this similarity with the dot product between the two vectors. Finally, to ensure that the weights are positive and sum to 1, we pass them through a softmax operation. The softmax is applied over all weights for the current output yi. Here's an illustration of the computation. For the output at position 3, we compute all dot products of an input vector xi with the input vector that corresponds to the current output. So note that x3 appears in all of the dot products, and all the other vectors appear in only one of them. These are the raw weights. We then softmax over all weights we've computed to make them positive and make them sum to 1. Then we multiply each vector by its weight, and we sum up the results to get y3. Self-attention looks particularly simple when vectorized, that is, expressed in terms of matrix operations. Note first that if we arrange all the weights for one output vector, say y1, in a long vector, w, with one element for every input, then the computation of the weighted sum for y1 is just w times x transpose. where X is a matrix containing all the input vectors as columns. If we then do the same for the other output vectors, and concatenate all these into a matrix W as its rows, we see that the multiplication W times X transpose computes a matrix Y transpose, where Y has the output vectors as its columns. Next, we need to figure out how to easily compute this matrix of weights W. We'll start with the matrix of raw weights W prime. The element ij of this matrix is the dot product of two vectors, I and j. This is essentially the definition of a matrix multiplication. This means that if we set up one matrix with xi as its ith row and one matrix with xj as its jth column, multiplying these together will give us W prime. The result is that W prime is equal to X transpose times X. Finally, we need to apply a softmax. This should go over all the weights that correspond to a single output, that is, the rows of W prime. Therefore, we apply a row-wise softmax to ensure that in W, all the rows sum to 1. And with that, we have the 3 steps of a vectorized simple self-attention. Here are some things to consider about the self-attention operation we've now defined. First, in general, we can expect the dot product of a vector with itself to be bigger than the dot product with any of the other vectors. This is because the dot product is roughly a measure of similarity, and a vector will usually be most similar to itself. This means that the weight Wii will usually be much bigger than the other weights. In short, for output yi, self-attention usually produces a mixture of the input vectors that consists mostly of xi, with a little bit of the others mixed in. This means that the output won't be that much different from the input. This is not necessarily a bad thing, but we will add some ways to change this later. Second, note that simple self-attention, as we've defined it now, has no parameters. The only way we can steer how self-attention behaves is by controlling the input values. For example, we can feed self-attention with embedding vectors, or feed it with the output of another layer. We'll add some parameterized components later, but for now, it's important to realize that the fundamental operation of self-attention does not have any parameters that we can control. Third, note that if we treat the matrix W as a constant, the self-attention is a linear operation. It's just a matrix multiplication. This means nice non-vanishing gradients. Of course, W isn't constant, so we essentially get 2 paths of computation between X and Y. One linear, with clean, fast-acting gradients, and one nonlinear, with slow, vanishing gradients, but able to learn nonlinear operations. It's likely that this is where a lot of the power of the self-attention comes from. Compare this to the LSTM, where we had a conveyor belt which was only affected by linear operations, and then a set of nonlinear functions that drove the manipulation of the conveyor belt. The principle here is very similar. Here are 3 more points to pay attention to. First, note that the self-attention has no problem looking far back into the sequence. In fact, for a sequence of 1000 elements, the input x1 influences the outcome y1 in exactly the same way as it influences the outcome y1000. The information travels exactly the same distance along the computation graph. Compare this to an LSTM, where the information in x1 goes through one cell to compute the output y1, but it goes through 1000 cells to compute the output y1000. In fact, the self-attention doesn't really see the sequential structure of the data at all. When an LSTM computes the output for y6, it can treat x5 differently from x1, even if x5 and x1 are the same vector. It can use the position in the sequence in addition to the content of the vector. Simple self-attention cannot do that. For this reason, we say that it's more of a set-to-set model than a sequence-to-sequence model. This has its benefits, such as the first point in this slide, but it also has certain downsides. To get the best of both worlds, we'll see a way of introducing position information in the next part of this lecture. Finally, the self-attention is permutation equivariant. This means that if we shuffle or permute the input sequence, the output sequence will be shuffled in the same way but will be otherwise unchanged. In many ways, these 3 points are different perspectives on the same thing. As a simple example, before we move on, let's build a sequence classifier consisting of just one embedding layer, followed by a simple self-attention and a global max pooling layer. We'll imagine a sentiment classification task where the aim is to predict whether a restaurant review is positive or negative. If we did this without the self-attention layer, we would essentially have a model where each word can only contribute to the output score independently of the others. This is known as a bag of words model. A naive Bayes model and a zero-order Markov model are other examples of bag of words models. In such a model, the word terrible would probably cause us to predict that this is a negative review. In order to see that it might be a positive review, we need to recognize that the meaning of the word terrible is moderated by the word not. This is what the self-attention can do for us. If the embedding vectors of not and terrible have a high dot product together, the weight of the input vector for not becomes high, allowing it to influence the meaning of the word terrible in the output sequence. This could help the model learn, for instance, that the negative sentiment carried by the word terrible is flipped around to a positive sentiment by the word not. The model cannot yet see that the word not is close to the word terrible, or understand the grammatical relations in the sentence, but it can at least see that this sentence contains both words, so that it might want to hedge its bets on calling this a negative review. The standard self-attention, as it's normally used, adds some bells and whistles to this basic framework. Specifically, these 3 features: scaled dot products, key value and query transformations, and multi-headed attention. Scaled self-attention is very simple. Instead of using the dot product, we use the dot product scaled by the square root of the input dimension k. This ensures that the values of the raw weights don't blow up if we increase the dimension of the embedding vectors. These are inputs to a softmax function, and large inputs to a softmax cause extreme values in the resulting probabilities, which often corresponds to poor gradients. So we want to keep these raw weights from blowing up. Have a look at the lecture notes if you want to know where this square root of k comes from. Next are keys, queries, and values. In each self-attention computation, every input vector occurs in 3 distinct roles. The value is the vector that is used in the weighted sum that ultimately provides the output. The query is the input vector that corresponds to the current output, matched against every other input vector. And the key is the input vector that the query is matched against to determine the weight. This is where we'll add some parameters. We will manipulate the input vector based on which of these 3 roles it appears in. We can see where these names come from by comparing the self-attention operation to a dictionary. Here is how that is written in Python. A dictionary consists of keys and values, and we can set or retrieve a value from the dictionary by passing it a query. The query is matched against the key, and the value corresponding to a particular key is returned. In a dictionary, all the operations are discrete. A query only matches a single key and returns only the value corresponding to that key. We can now define an attention operation as a softened version of the dictionary. The attention holds a bunch of values, which are vectors, and to each value is associated a key, which is also a vector. We can then ask the attention to give us a value for a given query, which is again a vector. Where the attention differs from the dictionary is that the value vector it returns isn't just one of its values, but a mixture over all of these values. Each value stored in the attention contributes to this mixture to some extent, based on how similar the query is to its key. We can now say that simple self-attention is just attention, but with the keys, queries, and values taken from the same set. To make self-attention a little more expressive, we can give each vector xi a small transformation just before we use it. We then apply different transformations depending on whether xi will be a key, query, or value. This allows us to subtly change the behavior in different ways. Here's how that is done in practice. We multiply each input vector by 3 different k by k parameter matrices, which gives us a different vector to act as key, query, and value. We've also given each transformation a bias here. In recent models, people report good results without these biases, using just the transformation matrix, so they may not be strictly necessary. Consider them an optional addition to the self-attention. Finally, we will move from self-attention to multi-head self-attention. Fundamentally, the idea is just that we apply multiple smaller copies of the self-attention, called heads, in parallel, each with their own key, query, and value projections, so that each can behave differently. One way of thinking about this is that in many sentences, there are different relations to model between words. Here, the meaning of the word terrible is inverted by not and moderated by to. Its relation to the word restaurant is completely different. It describes a property of the restaurant. The idea behind multi-head self-attention is that multiple relations are best captured in different self-attention operations. To implement this, we apply H self-attentions, each with different K, Q, and V matrices and biases, in parallel. In this diagram, we see that there are 4 attention heads, that is, 4 different self-attentions applied in parallel. This is usually done in a way that requires roughly the same number of parameters as one single head self-attention on the same input. To achieve this, the data is projected down to separate keys, queries, and values of dimensionality k over h, or in this case, 1/4 the size of the input. Each of these smaller inputs is then fed to a separate self-attention, and the results are concatenated. If you implement this cleverly, you will end up with exactly the same number of parameters as the original single-head self-attention, except for the additional W0 matrix at the end. So that's self-attention, a sequence-to-sequence layer that gives us parallel computation and perfect long-term memory. It's fundamentally a set-to-set layer. It has no access to the sequential structure of the input, and a large part of the behavior comes from the parameters upstream.